the sun. The sun gives us heat, it gives us light, it gives us energy, it helps plants grow through photosynthesis, it can give us sunburns which aren't good, but like, what actually is it? Like, what is the sun? Well, it's not a big ball of fire as it kind of looks like. What it is a big ball of plasma. Now, if you know about your states of matter, you will have heard of probably solids, liquids, and gases. After gases comes another state called plasma. And that's what the sun is. It's a big ball of plasma. And it's actually what all the stars in the nighttime sky are as well. You might have heard that the stars and the sun are the same thing. That's true. They're all balls of plasma with different sizes and different temperatures. Let's talk about what plasma is really quickly. So we know about the states of matter, so solids, liquids, and gases. Solids, the atoms, so the things that make up everything, are all clumped together. Liquids, they roll around each other, and in gases, they float away. Plasma's like a gas, so the atoms inside just float away, they do. But the difference is, with part of the atoms, the electron is disconnected in most cases. It's disconnected from the actual atom. So you have ions, which are particles without electrons, and electrons that float around in this soup called plasma. So now that we know what the sun is and what the stars are, how do they work? Well, they work on a process called nuclear fusion, which basically means you get two small things and you combine them together to make one bigger one. And when you do that, energy is released. So in the case of our sun, you get two small hydrogen elements and they combine to form a bigger helium element, and then energy is released. And this process happens trillions of times every second. And because it happens so many times every second, that energy all adds up and you get a heap amount of energy, and it expands and it pushes out and it comes out of the sun, and that's how we get the heat and the light and all the other forms of energy or radiation from the sun. Now, there's something that keeps the sun stable, keeps it together, because we've got this fusion that's like pushing out the sun, right? So what's balancing it? Gravity. And so the balancing, so this pushing out and pushing back in, this process is called hydrostatic equilibrium, which basically means that the outwards pressure of the sun to expand and to also push the nuclear fusion to push the sun out is balanced by the gravitational pressure that keeps the sun together. So kind of like this. So here's the fusion. So you have the two hydrogens or the two whatever, and you combine them to make one bigger one, and you get energy. Hydrostatic equilibrium, you have this internal fusion pressure, as well as the fact that this is plasma, so it's like a gas that wants to expand, but you also have the gravity that's collapsing it, it's keeping it down. And that is how the star or stars stay together. Now you might have heard of a red giant, or maybe a blue hypergiant, something like that. Those stars are where hydrostatic equilibrium has actually started to break, and they've started to either expand or contract. And we'll talk about that in a moment. Let's get back to our sun. How hot is the sun? That's a good question, eh? How hot is it? Well, it's about 5,800 degrees Celsius on the surface. It's a lot. That's very hot. In the center of the sun, where the fusion happens, so the elements combining, it's somewhere in the millions of degrees Celsius. It might even be more. It's insane. It is. What color is it? Well, that's actually really interesting, because if we were to see the sun with our eyes out either in space, like with a spacesuit on, or even on Earth, it's actually going to be white. So the photo that's up right now, this is a photo of our sun, but it's in UV light. It's in ultraviolet light. So it's not in light that we see with our eyes. We see with visible light. If we were to look at the sun with visible light, either from space or from Earth, it would look like that. That's what the sun looks like, nice and white and like a sphere, not with anything ejecting from it. It's pretty interesting. When I first saw that, I was like, whoa, no way. What about the age of the sun? How old is it? Well, it's about 4.6 billion years old, and it's got about another 5 billion years left to live until it dies. So why don't we talk about how it's going to die? Oh, one thing. Are there different types of stars? Yes, there are. So there's this diagram called the HR diagram, which describes what stars are and different types of stars it does and where they are in their life. Our star, our sun, is a G-type star. It's a main sequence ordinary star. It's classified as yellow, but we would usually see it as white or a little bit of yellow in our atmosphere. But it's an ordinary, normal star, nothing really significant about it. But eventually it's going to become a red giant, which we'll talk about the death of the sun, because that is where it becomes a red giant. So, voila, death of the sun. How great. No. So eventually the sun will die because it will run out of fuel. It will run out of that hydrogen to fuse together, to combine and produce that energy. So when it starts to run out of that pressure, that fusion pressure is not going to be as strong. It's going to diminish. And so the gravity is going to be able to collapse. So the hydrostatic equilibrium, that balance between the gravity and the outwards pressure, that's broken. Which means, and so the hydrostatic equilibrium is broken, and the star will start to collapse. As it starts to collapse, inside the sun, inside the star, it gets hotter and hotter and hotter because everything's collapsing onto it and it's putting more pressure on it, so it's getting hotter. And so when it gets hotter, eventually it'll get so hot that it can actually start to fuse helium. That stuff that was created before by the hydrogen, that can start to combine together to form other things. And eventually when that happens, the sun will have a new spark of energy, it will. And it will expand out. In fact, it's going to expand so much, it's going to become a red giant. Don't worry about red for the moment. I'll talk about that in a minute, why it's red. But it's going to become a giant star. And it's going to become so big that it will actually swallow up Mercury, Venus, and most likely Earth. It will swallow all of the planets, all of those planets up. Crazy. Now, eventually the helium's going to run out. And when the helium runs out, what's probably going to happen to the sun is that it will then, will start to collapse again, but it won't get hotter for anything else to burn. So the gas or the plasma that's there will just disperse out into space. And you'll be left with a white dwarf star. Almost forgot what that was. Now, why is it red? So if you've ever heard of, here's a quick question. What's hotter, a red flame or a blue flame? Well, if you know the answer, you'll know that it's a blue flame. And that's because, based on the electromagnetic spectrum, so the colors of light, so red, orange, yellow, green, blue, indigo, violet, the ones on the red side are actually cooler in respect to temperature, and the ones on the blue side are actually hotter. That's the relationship between color and temperature. Pretty interesting to know. So a red giant is a giant star, but it's actually quite cool because it's gotten so big that the temperature of the surface has decreased. So therefore the color decreases and becomes red. Well, I think that's a pretty good brief overview of the sun and the stars, so hope you enjoyed. Thanks for watching. No maths anyway, no maths involved in this, so yeah, take it however you want.